Given the inevitability of collisions, which we know from the pigeonhole principle, we need to handle collisions. And the resulting data structure we're about to create is the famous hash table. So as you know, because of integer overflow, we are just stuck with some kind of collisions, right? So for example, the hash code for moo and yep might both be 718. And no matter how clever we try to be, it is absolutely guaranteed that we will have collisions, no matter what hash code function we write. So this is a problem, because if we're trying to do this data indexed array idea from before, well, when we look in position 718 and see true, we don't know if it's moo or nyep that we have. So what I'm going to propose, and my alternate big idea I'm just going to give away, is that let's say we have n items that all have the same hash code. Well, instead of storing a true-false value, we're instead going to store a bucket of items that have that representation. So for example, since moo and yep have the representation 718, well, if I want to know if moo or nyep are in my table, I simply go to that position in my array and then search the bucket of items that have been inserted. Now, I haven't told you what this bucket is, but it could be anything. It could be, for example, a linked list. It could be an array list. It could be an array set. In fact, it could be pretty much any kind of collection which you can iterate over and look for things. Okay? So that's the heart of the idea that we're going to develop now into the hash table. So let's make sure that this is very clear what I mean here, and I'm going to specifically use the idea of a linked list bucket. Okay? So this is a little demo showing how this might work if we have linked lists. So we have an array of linked lists, and initially, these are naked recursive linked lists, and so initially they're all null. But then when I come along and I add a, we create a new list that contains a and link it up from that position. Next up, maybe we try and add abomemara. Well, we compute the hash code, we go to that position, and since bucket h is currently empty, we're going to create a new list that contains x and store it there. Now if we go and say add a devilish, well, it turns out to have that same hash code. So we're going to go to that list, so the bucket is already a list. We're going to add x to the end of the list if it's not already present. Or we could add it at the beginning, either way. Next, if we try and add abomemara, well, nothing happens, because we would look up this hash code, or we'd compute it, we'd look up this position, we would iterate through the list, and we'd see abomemara and say, I should not continue adding anything. It's already there. So this approach, we might call it a separate chaining data indexed array. And the reason I'm calling it this is that each bucket is a separate chain of all items that have that same hash code. So now if we try to do lookup, for example, like does this contain a devilish, well, we will compute this hash code again, 111239443, go to this little list, and we see that, indeed, a devilish is present. So that's the heart of our new, better idea. So let's improve it. Before we improve it, let's first look just very briefly at the performance. So if we think about the performance of one of these separate chaining data indexed sets or data indexed arrays, it's going to, instead of having constant time operations, it's going to have theta q operations. What's q? Where q will be the length of the longest list. And here I'm specifically referring to the worst case time. So in other words, with our old data indexed arrays, it's just a simple is it true or false to get the contains operation. But for our separate chaining data index set, well, if the list is of size q, I'm going to have to spend q time finding that item. Now I should note that the insert or add operation is also going to be theta q. It is not 1. So you might think that I can just go look up the hash code and then stick the item at the front, but recall that we're not going to add an item if it already exists in the list. So when we're inserting, we still have to walk through the entire list, and since I'm using a separate chain that consists of a linked list, that is going to be theta q. All right. So now that improvement that I was promising. Well, I'm going to observe that we don't really need billions of buckets. Okay. So I here have, maybe 2 or 4 billion buckets, but I'm going to say, what if I just had 10? What should I do? So that's a question for you, actually. If I have these 5 items with these hash codes, where do you think those 5 items should go if I only had 10 buckets instead of billions? So use your intuition. Do something that feels right. Okay, so what I'm going to do is I'm just going to stick it in the bucket that has hashcode mod 10. So for example, for B, I'm just going to use this last digit, and it's going to end up in bucket 8. Cat has a hash code ending in 4, so if I mod it by 10, it ends up in bucket 4. If I have dog, which has 8, well, it also ends up in bucket 8. So whereas before bee and dog used to be separate, now they are together. And the short version of that is simply that I'm only using the last digit of my hash code. Now, is that somehow dangerous? We'll talk about that a little bit later at the very end of this lecture, but just conceptually, it should be fine. The obvious downside is that my lists will now be longer. For example, the list that B is part of is no longer size 1, but now is size 2. Okay, so this approach, though, at its heart, is a hash table. So what we've created, it basically works as follows. We take some data, like this Chinese that I think says something like bao bao. I don't know the tones, but and then we do Unicode to int on this, okay? If that's my hash function. In that case, I get back a hash code, which is this long number. It's 1 billion and something. And so ultimately, the first part of the process is we take our data, we convert it using a hash function into a hash code, which is an integer representation. And then lastly, we then reduce that hash code to a valid index. And often we'll do that using the modulus operator, but we'll see in Java we have to do something slightly different in order to handle negative hash codes. So here, whenever I reduce it by modding by 10, I get the index 0, and therefore bao bao is in the hash table at position 0. So that's it. At this point, we understand hash tables, and that's great. That's all they really are. It's a simple idea, and it turns out they're really great. Now, there's still some details we need to discuss about how to make sure that they're efficient, but that is the hash table that you will come to know and love.